So thank you very much for the introduction. I am Yamshid Farhat, Head of Technology at Enda Prime by BKW. Maybe as a short introduction, BKW is one of the biggest energy utilities in Switzerland, and I'm at the Power Grid Group, where we plan and operate the distribution network for Bern, Jura, and Solothurn. During these days, I've heard a lot about how AI is the biggest revolution since the industry revolution, but I would like to start with even a bigger change for us, and this is, of course, the climate change that it will disrupt everything that we know, and especially it will disrupt the energy systems that we have today. For the electric network, at least, what we are expecting for the next 30 years is that we will require the decarbonization of our network, so all the production should be CO2-free emission, and we are also expecting the electrification of the transportation and the heating systems, as was presenting before. So in order to present a bit the challenges that network operators are facing, I would like to start with a short introduction how the networks have been working for the last 100 years. Before I start, I would like to comment maybe two ugly truths that I have found quite interesting, especially after the speech that Google did today. First of all is that some experts compare the electrical network with the communication network, where probably we would expect that with the telecom network, if the network cannot handle a specific moment of congestion, we can comment as, for example, the pandemic time on 2020, the quality of the communication will get reduced for everybody. On the other hand, for the electric network, it's not that same case. For the electric network, a congestion or a moment where the production doesn't match the consumption will lead to instability that will put at risk the whole system and probably could lead even to a blackout. On the other hand, today was really interesting to hear from Google how their data centers are almost 95% CO2 free, but that doesn't mean that the network infrastructure could be reduced thanks to this 95% CO2 free. Probably even the required network infrastructure for the Google data centers is much more higher than before, because now the network operator needs to be able to ensure the integration of these big PV solar parks and wind parks, while at the same time, the data centers in winter, in the single days, this 5% of the time that there are no enough solar production, there's no enough wind, they will still require the same power from the grid. So as a basic introduction, the network today, it works as follows. We have intelligent on the transmission network, where we have low number of nodes, where we measure basically everybody and every single point of connection, and we have there a redundancy in measurements. On the other hand, we have the distribution network that connects every single customer, where we are almost blind. Now we are starting with the smart meter rollout, but basically we don't have any type of measurements in this area. How the system works today is a transmission network operator in Switzerland is Swissgrid. They control the production, especially so the production follows the demand, in order to ensure the stability of the system. At the same time, distribution network operators plan the network for the worst case scenario. That means that even that there is one tree that falls in a big line, the system still runs stable, and we can provide electricity with a good enough quality of supply for every single customer. Regarding the energy transition, we did not yet change our methods to plan the network, but we are already seeing the changes and the challenges on our system. For example, we find quite interesting at BKW, we are a network operator that since the 19th century, we push really hard for hydropower plants. And in 2020, we reached a milestone for us. This milestone is that since 2020, and in just 10 years' time, we have more installed solar power in our network as hydropower. And this, of course, is just the beginning. If we consider the expectations of the Swiss energy strategy for 2050, and we compare it with where we are today, the yellow line is existing hydropower plants at the network, and the blue line is what we are expecting of solar power during the next years. And in addition, as we were mentioning before, we should also consider the electrification of transportation and heating system. Which impact had this on the network that we know today is that we have a complete different structure. The transmission system operator that until today has been able to control the power plants to match the required demand in real time, he won't really be able to do it anymore. And the question is, should be connected to millions of actors who put the network at risk? In that case, of course, we will require a gold distribution network, or should we think about new methods, new type of networks that enable a more efficient and more robust system for the future? In this sense, of course, AI and machine learning plays a really important role. But before we start to consider which applications are possible for machine learning and AI, I would like to come a bit as the pessimistic guy. What are the challenges that makes kind of hard at the moment that we can profit from machine learning in our power grids? First of all, it's important to clarify the effect of unbundling and that power grids are a totally regulated business. In this sense, even in a liberalized market, you would be able to choose your energy provider, but you will never be able to choose your power grid provider because, of course, it will depend where you are located and who is the owner of the network infrastructure. On the same time, for other business, 99% efficiency, 99% reliability, it would be really good KPIs, really good numbers. For power grid operators, of course, that would mean that 3.5 days per year, you wouldn't have electricity. And that, of course, for 100% of the citizens of Switzerland, at least, that would be totally unacceptable. So reliability will be always the key in any type of decision. On the other hand, we need also to accept that the network is today planned by engineers, and engineers always tend to transform stochastic, probabilistic problems into deterministic problems. So they can clarify why this or this decision has been taken. What that means that there is really a fear to black boxes in this term. In this sense, machine learning or AI, where an engineer cannot really understand or cannot really explain why this decision has been taken instead of a more traditional decision. On the other hand, power and energy are totally separated at the moment. The network planner is not in contact with energy providers, and network planner just care about the instant power that flows for every single cable. In this sense, it means that we always plan the network based on the worst possible case scenario. And that, of course, means that the investment that we are expecting for the future will massively increase. In fact, we worked together with University of Geneva in the past, and we could make some models that show that at least we believe that 11 billions will be required just in Switzerland in order to handle or to upgrade the existing network to enable all this massive integration of new actors on the local level. So maybe more on the side of machine learning and AI, where are we at the moment for power grid operators? At the moment, we are starting to generate more value with machine learning, but especially we are starting to generate more information for engineers. So basically, we are trying to use the existing data to build models that provide insightful inputs for our experts so they can take the decisions with their traditional methods. In this sense, for example, here I present an example where at the moment at our network we have around 10% of customers with the smart meters, and we are using an MLOps process where we are taking these 10% of smart meters, we are clustering them, and we are getting also the customer information for every single customer in our network. And through a classification model using random forest algorithms, we are able to tag every single standard load profile that we generate with every single customer. And in this sense, we can provide to our engineers a model, a data set where they can analyze every network with enough information of every single customer. And on the other hand, on the more operation side, we are also generating more value using computer vision. We are already starting to identify automatically defects on assets, where analyzing pictures done by drones or helicopters, we are able to automatically identify if an insulator is broken, if there is a scratch on the pole, if there is corrosion. And at the same time, more on our back office level, we are starting to automatically analyze documents in order to automatize processes that until now were really requiring a lot of resources from our side. But of course, we are seeing that all these quick wins that we are working at the moment are not really an end-to-end process. We are not really generating additional value from artificial intelligence in the sense that we are just generating inputs for our engineers to continue plan the network as they have been doing until now. As an advanced wins, I took the freedom to include in my presentation a work done by the University Polytechnical of Catalonia, where they interestingly review the different applications that at the moment are possible thanks to AI and machine learning, where they go one step further, and now it would be possible to take decisions directly based on machine learning models, for example, as predictive maintenance. Before we were showing that using drones, we can directly identify defects on our assets. We are also able to build a health model where directly identifies when and where should our inspectors check the state of our infrastructure in the network. But at the same time, when we see these use cases, I come myself with the question, they are disruptive enough? They are really disrupting the energy system that we know? Or they are just helping the network planners to keep planning the network as they are doing today? Because of course they will profit from AI, but the question is, will we be able to reach the goals that we have for 2050? And personally, I believe that it won't be possible. Therefore, especially at our group at Enda Prime, we are trying to propose our vision for the future of energy grids, where we are convinced about the energy cells concept that VDE in Germany presented in 2019, where we are trying to rethink the network from a centralized system that connects every single country in Europe and it's controlled by a central entity as a connection of millions of energy cells where every single cell is capable of optimize themselves, help their neighbor, and try to locally find the optimal state for the energy requirements at any single moment. So maybe as a short introduction, because of course the concept is much more complex than presenting in 15 minutes today. Important key of the cellular energy system would be that a cellular energy system knows its local state. It means that it has enough models to understand what is the production, the consumption, the requirements on a single state, but at the same time in the next 24 hours or 48 hours. It is capable of optimized based on their existing actors and based on the existing requirements also from the different actors in Switzerland. It also is capable of, through a P2P communication, support and trade with a neighbor in order to reach a common optimal state. And at the same time, of course, it's also able to coordinate with the network operator in order to ensure the reliability of the system. And of course, as a step further and let's say take a bit out responsibility from the network operator, if everything fails, it's no longer necessary that the network operator build a gold network. The energy cell is responsible itself for this survival mode and to decide what it would be required to deal in this worst case scenario. So, as already tell, in this sense, AI will play a critical role on the energy cell system, where we will require advanced forecast model, advanced state estimation, we would require advanced local optimization, but we will also require advanced dynamic models, not for energy pricing, but also for dynamic network pricing. And of course, we will require decentralized and advanced agent-based P2P markets. And in this sense, also, we are aiming to profit from work done by University of Geneva, as presented before, where this modeling forecast is not just aiming to give expectations for the future, but it also can help to proactively plan what is the optimal local energy generation that would be required for local energy cells. So as a conclusion, these days we are talking about digitalization a lot and the potential that we are seeing using AI and machine learning. We are seeing, of course, that decarbonization is the other big challenge and revolution that we will have to face during the next years. And especially during the events that are happening at the moment, we are also experiencing the importance of democratization or sovereignty, or let's say independence from external factors, as could be the gas prices or the geopolitical things that are happening and could happen in the future. And of course, in this sense, we believe that this energy cell concept, it's really the fit in this triangle, the center or the potential solution that could work on the future. And at the same time, these three fields could be transformed in three actors, and we could say that research, industry, and policymakers should work together in order to reach this, because at the same time, it's not possible for a single actor to reach this. So to end my presentation, I would like to use the quote, I believe it was from the CEO of Octopus Energy, that he said he compares the energy transition with a chess. And we say, we are trying to model the future, we are trying to discuss what are the optimal policies for the challenges that we are facing, but the reality is that as in a chess game, we don't know where we will be after 10 moves. So instead of discussing what is the optimal solution, what are the optimal models that enable us to understand our requirements, let's make our first move. Let's start already to find out in which direction we should go, and then we see what we have learned from this move and where we want to step forward. So thank you very much. I hope that you find my presentation interesting, and I'm willing to answer your question right now or later during the conference. Thank you very much.
Thank you for this really nice presentation. I already see the first question. Sorry.
Thanks. Thanks for the talk. I actually have two questions. What do you expect these energy cells, what size do you expect these energy cells to be? Will there be like one house with solar panels, or will it be more like a collection of house, a neighborhood, a village, a town? The scale you expect? And the second question is more on how do you expect these cells to communicate together, this P2P communication? Do you think it should be through the electrical network, or do you think they should all be connected to internet or to wireless network? So.
That's a really good question, thank you. So regarding the energy cell size, of course, it will be based on so many requirements. And from my point of view, I would say that the size should be optimized based on the number of actors that are included on this energy cell. If, let's say, a house just include, let's say, a consumption and a solar panel, probably it will be too small to be able to be optimized and could be integrated in a bigger energy cell, let's say, is a urbanization where they can optimize their system together. But maybe an industry that has already consumption, production, and flexibility could already profit itself from an energy cell. Regarding the second question, this is a really important topic because I believe that the P2P or the connections between energy cells should be independent from the network operator. This is important because especially the existing SCADA system or the existing network operator system, it has a huge requirements on cybersecurity. And of course, it wouldn't make any sense that a single solar panel owner has the same cybersecurity requirements at a nuclear power plant. And in that terms, I believe that we should look in an alternative local level P2P layer. And this, of course, we are willing to talk with other industries, other research groups that has much more experience, maybe in a blockchain level or in another system that have much more advantage than the existing network operator communication system.
Thank you.
Thank you for the talk. My question is about an issue you mentioned at the beginning of your presentation. You talked about the distribution grid, and you said that we are basically blind with respect to that. In the academic community, many people are trying to solve this by applying machine learning method on data collected on the nodes of the distribution grid in order to infer the topology and the electrical parameters of the line. I would like to ask you if this is an issue also in the industry, and if yes, which kind of approaches are you applying in order to solve the problem? Thank you.
Thank you very much. So basically, until now or before the energy transition revolution, it was not a problem because it was easy to get the last measurement at the substation, distribute it by all the customers that we have after it, and make a worst-case calculation and plan the network for the worst-case scenario. The over-designing factor was not that so big. Now, of course, based on the massive amount of solar energy, solar panels that are located on the low-voltage network, increase the complexity. And of course, we are we are aiming to deal with it through a smart meter rollout. So we are hoping that by 2028, we will have almost 100% observability, at least by the end customer side. And using this information, using different models, we would be able to aggregate this information to have, let's say, a full observability of the distribution network. But the challenges for network operators remain the same. If the network should be planned for the worst-case scenario, then the benefit of this data won't be that huge. So in this sense, we are aiming to rethink on the existing topology because, in my point of view, in this topology, even with measurements, you don't really bring an added value to the system.
Very good talk, thanks. You talked a lot about maybe the technology and so on. How is the regulatory situation in Switzerland? Is it already possible to implement such energy cells, or what are the problems there?
That, of course, is a really good question. Of course, is basically the bottleneck for this type of solutions, because basically, at the moment, nobody has interest in this type of solution from a regulatory perspective. Network operators at the moment are not, let's say, asked or request to optimally plan their network. At the moment, the existing regulation is financing the network upgrades for every single new PV installation. So basically, network operator doesn't really care if he's upgrading the network in an optimal sense or he's just over-investing on the network, because from his asset management point of view, doesn't make any play. Of course, as we were saying, as I tried to comment at the end, this type of solution, it won't be possible if research, industry, and policymakers don't work together. Because at the moment, I need to be a bit critical, we are not going in the right direction. The existing discussions with regulators are focusing on the new network tariffs that focus on power instead of energy, are focusing on being able to reduce the maximum power that PVs feed in the network from 100% to 70%. But based on the requirements that we are facing, that it's not even scratching the surface of the problem. So there we will need much more proactively and not just discuss what is the optimal solution, but do something already today in order to face the problems that we are going to deal the next 30 years.
Mm-hmm. Okay, thank you. And can you already implement some energy cells in research projects or so on, which are kind of out of the regulatory frame, or?
We are aiming to start to plan energy cells. Now we are working on optimization algorithms and advanced models that enable to plan an optimal building that we are, of course, considering a building as an energy cell, because from the regulatory point of view, from the business point of view, it doesn't make really sense to plan let's say, urbanization as an energy cell without personal interest on reduced CO2 emissions, on sustainability factors. And the goal would be until the end of the year to start planning energy cells, and from next year start operating them. And of course, in parallel, trying to find synergies with regulators, with research partners in order to plan the future, the next steps.
Okay, but if you have some working examples, that might help. Yeah.
Exactly.
Okay, yeah.
That's
very
correct.
good. Thank you.
Thank you very much.
Thank you. As you said, switching to decentralized energy cells is pretty disruptive, and in most countries, the energy production is still vastly centralized. Do you have an idea of the threshold at which we should really switch to this decentralized energy cells? Like, is it 50% of the energy coming from decentralized sources, or even if we have 10%, it's still critical? It's already critical.
That is a really good question, and of course we are using Switzerland as our ecosystem to build energy cells. As you correctly say, the decarbonization should not be local or decentralized. Other countries are planning huge solar parks, huge wind parks, where these local energy cells does not really fit with these requirements. In Switzerland, the decarbonization will be local because basically there are so many challenges for wind parks to be installed in Switzerland, also for solar parks. And our models or strategy are really going on the local level. So we expect that, I believe 80% of the new generators will be installed a low voltage network. And there, of course, for Switzerland, it really makes sense, this disruptive paradigm change to energy cells. For other countries, your question is really good. I'm not capable to say a percentage, and I would like it to formulate it as an optimization problem, right? In which sense a local optimization brings more advantage than a centralized control of the system. And of course, regulation and external factors and each country factors are really important in order to evaluate that.
Okay, thank you.